Hello, dear colleagues. My name is Ostroumov. I am from National Aviation University, Air Navigation Department, and today I would like to represent you our results in scholar investigation of risk of mid-air collision in a lateral plane. As you know, mid-air collision it is a quite important event which probably in future will not happen. But the main problem of mid-air collision at first was faced in early 19 due to high speed development of aviation and of course lack of digital equipment on board of aircraft which can predict some mid-air collision. Of course, wide usage of these digital automatic systems reduce risk a lot. But nowadays we have a plenty different system into the ATC side and inside of each aircraft and of course in cockpit. That's why with the help of all of this automatic system we reduced a risk of mid-air collision how much it is possible, and according to statistics from IATA we've got that for period from 2014 to 2018 we've got only one accident that has happened. But of course each accident is quite important because usually in mid-air collision we have both airplanes involved. It means that it will be catastrophe of two airplanes and probably it will be very dramatic situation. That's why a problem of mid-air collision highly important in current aviation safety. But how we can estimate a risk of mid-air collision? Unfortunately, this event we can refer to highly rare event because for 4 years it was only once in the globe. That's why if you would like to estimate a risk value for example for Ukrainian airspace, we don't have enough statistic to make a prediction according to their statistical data. But in this case we can use modern simulation tools to simulate air traffic. Then we can a little bit speed up our process, and then we will get some results of unintentional aircraft deviation and probably mid-air collision. And only in this case we can talk about risk and we can assess some values for this risk. For example, some probability values or probable number of collision during some period of time. That's why usually at first we are working with different statistics. That's why we estimate different aircraft trajectories. That's why in this picture you can see a lot of aircraft trajectories, and you can see the middle of this track. That's why in ideal all aircraft have to fly by line, but in real situation all of them is deviate a little bit. That's why we can estimate statistically this deviation. Usually in this step we use different probability density functions, which you can see here, and then by parameters of these probability density functions we can estimate probability of aircraft unintentional deviation from pre-planned trajectory, and then we can use it for risk of mid-air collision estimation. But before we will talk about risk, let's talk a little bit about separation. Because aviation is a little bit different from road traffic. That's why at first, to ensure required level of aviation safety, we use three types separation. That's why each airspace user have to be separated from other airspace user in vertical, horizontal and longitudinal planes. Vertical separation, it is a scheme by which airspace users can use some specific flight levels, and usually some flight levels directed to one direction and the next flight level directed to the opposite direction. That's why at one road in vertical plane we have a lot of layers which we call flight levels, and at each flight level we can perform our flight. And usually flight levels can be connected with particular aircraft by air traffic controller. Usually for flight levels below 219 we use 30 meters between airspace users, and up above altitude of 219 flight level we use double spaced 600 meters to separate all airspace users. Lateral and longitudinal separation may be different, but nowadays separation based on performance-based navigation requirements is highly used in modern air traffic scheme. That's why, according to that, we have a set of area specification from 1 to 10, and for each of these specification we have some values for separation. That's why for lateral separation, for example, for RNP1 we have 5 nautical miles, for RNAV1 7 nautical miles. What does it mean? It means that the horizontal distance between airspace users, for example in Ukrainian airspace, have to be 5 or 7 nautical miles. It depends on airspace type. And longitudinal separation minimums, you also can see here that for RNP 4 and 2 we have 30 nautical miles. Next, usually in tasks of risk estimation we use some specific aircraft models, and in this case the most suitable is box model. That's why each airspace user in risk simulation model can be represented as a box with a specific size, width, length and height, and this size we've got from our separation minimums, because in air traffic highly important that each airspace user use specific volume of airspace, and it means that no one else can be inside of safety volume of another aircraft. And usually this safety volume, it is a minimums of separation in some particular airspace. And in this case each box airspace user has particular components of speed, horizontal, vertical, and longitudinal, and a risk of mid-air collision in this case can be represented as a probability of overlapping or crossing of more than two boxes in space. That's why if you know predefined trajectories of airspace user and we know separation minimums, that's why we can create a boxes which realize like real air traffic, and then use it for risk estimation to get a probability of crossing two or more boxes in some particular airspace. According to ICAO documents, the most useful formula by which we can estimate a risk as a probability value of unintentional mid-air collision can be represented on this slide as the following. Oh, just a second. And this formula called Reich formula, because it was at first developed by Professor Reich. And in this formula we use two probabilities. That's why it is a probability of horizontal overlap of two airplanes and vertical overlap. And here we've got dimension and speed across these sides of dimensions. Okay, and in risk estimation, usually scholars separate two types of risks. Risk of lateral or horizontal overlap and risk of vertical overlap. It comes from different sensors for airplane coordinates estimation, because for lateral navigation usually we use global navigation satellite system, or in particular some navigational aids. But for altitude detection usually we use barometrical altimeter, and errors between two of these systems too high. That's why usually in aviation we are working with two different risks. Of course, at the end they can mix to get like total risk of mid-air collision, but in particular we are talking about risk of lateral overlap and risk of mid-air in vertical plane. And in this case, probability of lateral overlap can be estimated as a probability of airplane deviation out of predefined separation minimums. That's why if you've got probability density function of airplane deviation and we've got constraints for our separation, that's why we can get easily probability of aircraft deviation from pre-planned trajectory, and multiplication of two of these probabilities give us a probability of lateral overlap of two airplanes at the same region. In this case, as a probability density function, we use triple univariate generalized error distribution in the next form, because this distribution gives us the opportunity to take into account navigation system error component, flight technical error, which is utilized human factor influence into aircraft maintaining at the trajectory, and influence of highly rare events. That's why we called it probability density function of tail. That's why if we have a predefined trajectory of aircraft, and if we have a lot of realization of this trajectory, then we can rebuild our probability density function. And as a model of this probability density function, we cannot use just normal density function, because it does not give us opportunity to take into account errors of positioning system and errors of human operation, flight technical errors. And of course some rare event may occur, that's why we need to take it into account. That's why we use more complicated form of our probability density function to estimate our airplane deviation more precisely. That's why if we triple univariate generalized error distribution in the full form can be represented as follows. And here on my slide you can see description of all of these parameters which we will obtain by maximum likelihood method by statistical data. For numerical demonstration in our department, we use the data from automatic dependent surveillance broadcast concept. That's why, according to ADS-B concept, each airspace user has to be equipped with a special transmitter which can transmit in non-synchronized and in non-coding mode location report at some particular time. That's why everyone in space, in controlled airspace, have to be transmit their location from global navigation satellite system receiver located on board of aircraft. And these reports we can easily receive, then decode and obtain the data. That's why in this figure you can see my laptop with software defined radio and with one of our antenna by which we can receive air traffic above Kiev region. This data transmission use very high frequency spectrum, and it means that in most cases we can receive the data from airspace users in maximum range up to 300 nautical miles. That's why we can cover maybe a small part of half of our Ukrainian airspace. Okay, if we know location of each airspace user for particular time, then we need to compare their location with roads, because each airspace user have to fly at particular road. In aeronautical information publication of Ukraine, we have aeronautical map. That's why these roads, blue roads, it is roads where aircraft can be located, basically, if it is civil aircraft. We've got this road in digital format, and we can easily compare the closest point of location of each airspace user to the road. That's why we can detect deviation of each aircraft from predefined trajectory. And then we can record the data, how much more it is possible. That's why we've got 30 minutes data. This data was recorded at April 23 of 2019. Then we compare all airspace users location with roads map, and then we estimate aircraft deviations from predefined trajectories. That's why you can see that the value of deviation is quite highly valuable, because in some cases this deviation can be approximately 30 kilometers, not meters, from predefined trajectory. Okay, and next we move our statistical data to maximum likelihood method to obtain parameters of triple univariate generalized error distribution. That's why here you can see a result of our fitting process. And as example, you also can see result of normal distribution fitting. And you can see that probably to give us more suitable result, because here two columns indicate us about highly importance of positioning error, and all other mainly is a result of human factor, because it is a result of how aircraft have been coded to flight. Okay, that's why in our research we use digital database of flight routes, which use 331 waypoints in the Ukrainian airspace. Then all of these waypoints are connected by direct flight routes, which includes approximately 500 direct routes between one pair of waypoints. Then according to this database we can estimate the total length of our flight routes, and also in our experimental research we've got a learning sample with approximately 2600 measurements. Of course, Ukraine has not too congested airspace. That's why we've got not too much traffic. That's why we've got approximately 3000 measurements for 30 minutes of flight. Okay, and also in this slide you can see result of our fitting by maximum likelihood method of our statistical histogram. That's why coefficients in this to-get function we've got like this one. Okay, and after that, if you know probability density function of airplane deviation in Ukrainian airspace, then we can easily detect probability of aircraft deviation in lateral plane. That's why for different box lengths, lambda y in nautical miles, we can obtain different probabilities, because it is a result in integral. Thus, you can see that in Ukrainian airspace we've got AirNav 1 performance. It is the requirements for onboard navigation system. That's why you can see that according to normal density distribution, this probability have to be approximately 0.21, but according to triple univariate generalized error distribution we have 0.15. That's why we estimate more precisely probability of airplane deviation into the left and right sides of flight track. And finally, we put this data in RIS formula and obtain probability of mid-air collision for whole Ukrainian airspace based on statistical data that we have, and for box size which is in correspondence to area navigation performance of AirNav 1. That's why we've got risk of mid-air collision for Ukrainian airspace at the level of 0.84 multiplying with the 10 minus 7, which is quite rare event. That's why it is near impossible situation, but we can estimate, and this estimation based on live air traffic. And on my final slide you can see conclusion of our research. That's why thank you for attention, and I will be glad to answer any questions in comments or during the conference time. That's why thank you everyone. Hope to see you in conference.